Hello everyone, my name is Ma Yukang. Today we will talk about an important problem related to national energy security and border infrastructure. The challenges of forced heavy and brittle factor in ethical engineering. As we make strategic progress in the polar regions, extreme cold is more than just a weather test. It's a national level challenge. This is not an overstatement. Any small failure of ethical infrastructure may break energy supplies or even cause ecological disasters. Our project focuses on those two main threats under the ice and snow. First, heavy and brittle factor. Now I'd like to introduce our team. Our group number is A5. At first, our team have 6 members, but when we are having discussions, 3 of them didn't take part. Maybe it was because they didn't like to work with us. So now our team is made up of me, Xu Tianyue, and Duan Kenan. We are trying our best to offer strategic engineering solutions to these physical problems using interdisciplinary research in thermodynamic analysis and material science. So next, my colleague will explain the basic physical rules that guide our design in detail. He will talk about the small-scale world, especially the scientific reasons behind heat transfer and phase changes.
Next, I will introduce two key issues in Arctic bridge engineering: forest heave and brittle fractures of metal at low temperatures. Both directly affect structural safety and long-term stability. When water in the soil freezes, its volume increases by approximately 9%. Due to capillary action, water migrates toward the freezing zone and forms ice at the freezing front. As the ice grow, they generated the large upward force that lifts the foundation. Repeated freeze the cycles cause cracking and uneven settlement, leading to structural damage. At normal temperatures, steel exhibits ductile behavior and undergoes noticeable deformation before fracture. However, below a critical temperature, a ductile to brittle transition occurs. At this stage, the steel may fracture suddenly with little or no warning, which is extremely dangerous for loading-bearing structures such as bridges. Therefore, Arctic bridge design must address first heave in foundations and select materials that maintain good toughness at very low temperatures. This shows that engineering safety depends on a solid understanding of fundamental physical principles.
Today, I'd like to share our engineering solutions for Arctic bridge design and their far-reaching impacts. First, tackling the unique challenges of Arctic against forest heave. We adopt deep pile foundations driven into stable permafrost and drainage layers with non-swelling soil, and use elevated structures to reduce heat transfer. For mental brittle fracture, we select low-temperature tall steel, optimize the welding process, and eliminate sharp corners in design. Thermal management is key too. We integrate thermal flash passive cooling systems, and inserted foundation structures to maintain thermal stability. These solutions deliver significant value. They boost infrastructure safety, cut long-term maintenance costs, support polar research, and mitigate climate change risks. Sustainability is at the core. Passive cooling/energy use, extended structural life, reduce material waste, and minimum resource consumption aligns with green energy engineering principles.